I'm Charline Tessereau. I'm a postdoc with Peter Dayan in Tübingen, and I would like first to thank the organizers to give me the opportunity to present this work. It's a very new project, so I'm really excited to show you this data. And the data has been acquired by Feng Xuan, which is a PhD student in Northwestern University with Daniel Dornbeck. And this project also involves Jacques Meller from University of Bristol and Peter Dayan from Tübingen in Germany. And I'm going to show you today data about hippocampal traces of uncertainties induced by changes in reward distribution. And what we mean by uncertainty in this project is related to the ability of, to predict about rewarding outcome, about where our rewarding outcome going to be. So for example, if on your way from work to home, you find an ice cream truck and you find the same ice cream truck at the same location every day on your way from work to home, then you may form a very precise prediction on where the ice cream truck is going to be. Thus, when you arrive at this location, your level of uncertainty is actually quite low about the fact that you're going to find the ice cream truck. However, if one day you arrive at the same location and don't find the ice cream truck, then at this exact position, you may experience a very high degree of surprise that typically can lead to unexpected uncertainty, or is usually referred to as unexpected uncertainty in the literature, which is the set of unknown unknowns, and which are usually triggered by an observation that lies very far away from predictive bounds. However, if on your way to work, the ice cream truck always changes location, then you're not so surprised to not find the ice cream truck at the location that you found it the day before, for example. So essentially, you kind of got used to not being able to very accurately predict where the ice cream truck is going to be. And this is referred to as expected uncertainty, or known unknowns, and it's due to the fact that the world is inherently stochastic. So maybe you can learn something about the distribution of the ice cream truck location, but you can't avoid uncertainty in that case. So we're interested in the encoding of these types of uncertainty in hippocampal cells. And why hippocampal cells? So I probably don't need to reintroduce place cells because David did a good job to do that. But essentially, when we record in hippocampus while rats are running around, for example, in our track, we see some cells that are very active around a specific location in the space and not very active far away from it. And these are very robust neural signatures of episode. But these cells have more properties that are also interesting. And one other property is that they can also change the location of their favorite location with reward. And this is a subset of place cells only that track the reward, as shown here in this kind of illustration, that this cell always fires where the ice cream truck is. And so and another nice property of these cells is that they track changes with experience. So in this paper, they recorded cells around a virtual corridor. So it's essentially kind of the same than before, but simply in a virtual corridor. And if you now align all the activities of the cells along the track position from the start to the end, and you organize the cells based on their preferred location, as I've showed you here, then you get this what's called place map, which shows the population activity, and you can see that spans the whole range of positions from the start to the end. And when you change the visual environment, so this is what they did in this paper, for example, then you can obtain changes in the pattern of activities on the place map. So some cells stop being active, some cells change their preferred location, and some cells will change their firing rate. And in this project, we're interested in looking at the patterns of remapping of those cells influenced by uncertainties in reward location that we induced by switching the reward location around, so to induce different types of uncertainties. And so we can look. So this is how it looks like. So you have you can see on the top video the mice that is running around the virtual linear track, and the velocity of the mice is tuned to the velocity of the wheel is tuned to the velocity of the screen, and at the end of the track it's teleported back to the start. It can then leak for a reward, and while they do that, then we record the cells, and you can see a video of what this looks like. So this is activity extracted from calcium imaging, which measure the calcium transient of the cells. So all of these kind of shining episodes here are calcium transient of the cells. So this is what we extract, and then we can access the activity of the cell, the calcium activity of the cell from these videos. Oop. So we train mice in different degrees of predictability, so that of the reward location. So that some mice are used to some reward zone, a very narrow zone of reward, so that it's extremely predictable where the reward is going to be, and then we switch. It doesn't want to switch, actually. And we switch the reward to the end, to a location that is much further away suddenly down the track, thus hopefully creating... Do I not? I'm not sure. Do I have to do something magical to make it work? Thanks. Okay. Yeah. So, okay. So we have switched this reward location to a location further down the track, and thus creating unexpected uncertainty around the reward location in the mice. And another set of mice, another group of mice is trained on a reward location that changes every trial, but that is bound to a reward zone, thus creating expected uncertainty, so that the mice cannot very accurately predict exactly where the reward location is going to be, but the best that it can do is predict the boundaries of this zone here. And this is how the place map looks like on a stable condition. So this is after extensive training. And what you can see is that we get place cells that span the whole range of the track from the start to the end, and we see that the place map is skewed around the reward zone. So this has been observed before. We know that place cells tend to accumulate around reward location, and they also track the reward. And we can now look at what happens after the switch. So these are the same cells. Sorry, I forgot to mention that they are ordered based on their cross-validated maximum of activity, and this shows the normalized activity. So they are normalized based on their maximum of activity. So we can look at the patterns of the place map after the switch, and we can observe that before the previous reward zone, we see some place cells that are being preserved. And after the reward, so this is after the previous reward, we see that after the switch, the cells actually, some subset of those cells that fire after the previous reward follow essentially the reward, and now are active after the new reward location. So essentially the post-reward map is being rescaled by this change of reward location, and is tracking the reward location. And the zone in between, it's much harder to qualitatively see any pattern, which probably measures the uncertainty around the experience of the mice in these locations. So again, we can look at how quickly this map disappears. So this is again the average activity before, and in here I added the leaking pattern. So we train mice to have until they are really precise in predicting where is the reward. So they essentially start to leak slightly before, and they leak until they get the reward. And we can look at the last trial before the switch. So again, we can see a very precise leaking pattern. And what we can see is that the map looks more or less like the average, with the kind of stochasticity of what one would expect for a single trial recording. However, on the first trial after the switch, what we can observe is that the cells kind of behave normally until they reach the previous reward location. But at this moment, the mouse still don't know that the reward is not going to get there. And on the exact moment of the surprise, then the place map starts to be highly impaired, and the mice start leaking until they eventually get the reward. And once they get the reward, then we see already the appearance of this post-reward map as soon as in the first trial after the switch. So we can also look at how quickly the new map forms. So this is the new map with place cells after the switch and ordered based on their favorite location after the switch. And what we can see is that on the first trial after the switch, so again, the leaking pattern is extended. So this is the same that I showed you before. And we can see that the cells that are firing previously to the reward, they are already here, essentially. And then the zone in between is much more confusion zone until they get the reward. And then we can already see the appearance of these new post-reward cells. And we can track the evolution of the formation of this new place map as it goes. And as quickly as in a couple of trials, really, the leaking pattern becomes more narrow around the new reward location. And the place map starts to look more like what it looks like on average. So, as an interim summary, I've showed you that an expected switch in reward location induces a rapid change in the place map that affects individual cells differently according to their spatial tuning, so that the map in between the old and the new reward zones is mostly affected. But the post-reward map follows the reward. So we see those cells that seem to be firing always at a fixed location compared to the reward, and that are essentially being rescaled to the post-reward zone. And what happens now when we change the reward every trials? So we can first look at the average activities, and what we can see is that it looks much broader around the reward zone in particular. But once we align this activity to the reward location, so in here essentially we've taken the activities for all trials and just kind of switch things around so that this dot here is aligned, and this shows now the position, the activity of the same cells, but on the position aligned to the reward. And what we can see is that the map looks much more skewed here, showing that maybe we get some clear reward responsive signaling around just after the reward comes on. And if we look at individual cells, this is indeed what we observe. So this now shows, again, the activity along the position on the track from start to end on the x-axis. And on the y-axis is the trials of this session. And this shows the activity of a single individual cells for every trial of the session. And what you can see is that this cell seems to be firing always following in response to the reward. And this is even more clear when we align the activity to the reward, which clearly highlights that this cell has a very seems to have a very stable reward field. It's a little bit less clear, however, when we look at those maps, what's really influencing the activities of those cells much further away from this reward zone here. So they could be influenced by position only, or they could be also tracking some form of responsive activity. And if we look at individual cells, we actually find both. So we find clear cells that have a clear kind of stable place field as shown here. And we also find cells that are both modulated by position and reward. So for example, this cell, when we look at this, its activity on the normal position x-axis or normal position basis, what we can see is that it seems to have a clear position field. And now when we align it to the reward, we also see that it has a clear reward response field. And again, also earlier down the track, before the reward comes on, it's also unclear whether these cells are only position cells or whether they are somewhat predicting where the reward is going to be, maybe based on the previous reward locations or based on the start of the zone. And if we look at individual cells, we also find this conjunctive coding, so the co-modulation between place and reward. And we see this cell, for example, has a clear position field. And this cell is a little bit more complicated. So when we align it to position, what we can see is that this cell seems to start firing always at the same location in the space, so very shortly before the reward zone. However, if we align the activity of the cell to the reward, we can see that it stops, so it's almost never active after the reward has come up, showing that it's clearly a co-modulation between space that maybe triggers the onset of this cell firing and reward that maybe triggers the offset of this cell firing. So we're trying to understand the complex interplay between reward and position in hippocampal code. And for this, we use GLMs. So GLMs stands for Generalized Linear Models. And essentially, we look at position and reward, and we have 4 types of regressors. One regressor, so 2 types of position regressors. One position regressor that captures the activity before the reward, the activity that is position dependent before the reward comes on. A position regressor that captures the activity after the reward comes on. And a reward prediction regressor that essentially we define reward prediction at the moment as a smooth exponential kernel of the previous reward locations, but I'm happy to discuss this more later on. And a reward response regressor that just captures the reward in response to reward after the reward has come up. And what GLMs do is that they find the kind of best linear combination of this weighted linear combination of these regressors that will maximize the variance in the signal. And the predicted variance in the signal. So I'm just going to show you how I build one of these regressors, and then essentially the method stays the same for the rest. So for the position regressor before the reward, this regressor is basically built from different basis functions. They're all Gaussians, and each of these basic functions will capture the activity of the cells at a specific location in the space. And they cannot capture any activity after the reward. And the reason for that is that we're interested in potentially the reward location influencing the or calling another place map, post-reward map. Okay, and so this principle is the same for all the other regressors. And this is how it looks. So this is the GLM performance. So we measure the performance through the R-score, which can compute how much variance is captured by the model, how much variance of the signal is captured by the model. And usually for neural data, R-score of 0.1, because neural data is so noisy, R-score of 0.1 is considered really good. And we can see that out of 369 cells, so this is a histogram, so it shows the cells count for different values of R-score. And I put here some kind of accumulation of the cell count, so to say. And we can see that we have, out of this 369 cells, half of them that are, two-thirds of them that are very well kind of captured through these GLMs. And we can look at the single cell prediction. So this is, again, the data for this place cell that we've seen before. And this is the model prediction with R-score of 0.45, which is okay, I won't lie, is one of the best cells. But we can also look at the individual contributions to this regressor, to the model, by looking at the shape of the kernel or the shape of the regressors after fitting. And what we can see is that the model clearly captures the dependency of the position to this cell. So, okay, that's kind of easy maybe. And something that we can do also is looking at how much these regressors contribute to the goodness of the fit by comparing the R-score to the R-score without this regressor. And you can see that in that case, this cell can clearly be quantified, categorized as a position post-reward cell based on this measure of goodness of fit. Okay, maybe a more complex example, if we look at a reward place cell, what we can see is that the reward again, the GLM again reproduces very well the activity pattern of the cells. And we can also look at the individual regressors, and we see a much stronger response reward regressor than others. And again, we can then quantify the contribution of these individual regressors, showing that this cell is mainly, so the main contribution to the goodness of the fit is reward response. But what about a more complex cell? So this cell that has kind of a reward response field and also a position field, then we also find the same. So again, qualitatively, the model can reproduce the signal, but we also then can extract the individual component or contributions of position and reward, both visually by looking at the kernel, but also we can quantify this by looking at how well the model without this specific regressor explains the full fit. Okay, so for next step, we want to spend more time to investigate this reward prediction regressor that I haven't told you much about because we're still essentially working on it. And we want to characterize the change in the position and reward contributions over time. So both over slow time scales within a session and over fast time scales on a trial by trial basis. And we're going to do that, so we're currently working on it, is by smoothly changing, allowing the kernel to change on a trial by trial basis. And all of this in order to track uncertainty representation and its relationship with behavior. So as a summary, very quickly, I've shown you that drastic and predictable change in reward location induce a rapid and spatially localized remapping that affects mostly the zone between the rewards, and that highlights reward responsive activity. If we now look at expected uncertainty induced by changes at every trial, we can see that this reveals a dual reward and spatial reference frame in contribution to the place activity. And this interplay between reward and spatial is quite intricate, and that we can capture this interplay with GLM. With this, I'd like to thank again my collaborators and thank that has run the experiment. Thank you for your attention. Oops.